All right, thank you very much to the organizers for the opportunity to speak here and for this very stimulating workshop. So I will talk about correlated Chern insulators in twisted bilayer graphene, and if time permits, also twisted bilayer MOT2. And this talk will be entirely focused on the presence of an external magnetic field, although of course I'll try to make a connection to zero magnetic field results as well. So because I will be talking mostly about the physics in the finite external perpendicular magnetic field, I should review the formula that was already mentioned in this workshop, the Streda formula. So if we have a gap state, it must satisfy the formula written over here, where the n here is the areal density, and so for our purposes, AUC is the area of the Moiré unit cell. So the left-hand side of this formula is the Moiré unit cell filling. This phi here is the magnetic flux through the Moiré unit cell. Phi naught is the flux quantum, and then S and T specify our state. So if we have a plot of a gap in the density versus magnetic field plane, the intercept in the limit of small magnetic or vanishing magnetic field will give us this number S, and then the slope is set by this T. So these are rational numbers, and I will be referring to them throughout this talk. So if S is an integer and T is an integer, then we are talking about a Chern insulator. We can have a fractional S, in which case there is usually doubling or tripling or multiplicity multiplying the unit cell. And if T itself is fractional, then we are talking about fractional Chern insulators, or if S is 0 and T is fractional, then about fractional quantum Hall states. So throughout this talk, T will end up being integer. So let me review some experiments. This is not going to be an exhaustive list, which report correlated Chern insulators in twisted bilayer graphene. And let's start near the magic angle. This is the data from Ali Yazdani's group, where the x-axis is the filling of the narrow bands. 0 is the charge neutrality point, and the y-axis is the flux per unit cell. What they plot here are the gaps that they see in STM. And then, as you can see, there are these prominent Chern insulators, which are emanating out of the charge neutrality point. This would, for example, correspond to S equal to 0 and T equal to -4. And then in steps of 1, they get up to T equal to +4. There's an 8 and 12, so fourfold degeneracy. And then these are the states which have a non-zero S. So the intercept here is 1, 2, 3, with the slopes 3, 2, 1, and similarly on the Hall side. So the states which are prominent in this data, apart from this quantum Hall ferromagnetism happening at the charge neutrality point, with non-zero S, are S plus T equal to -4 or S plus T equal to 4. And I will focus on those throughout this talk. This has been seen in other groups. This is from Andrea Young's group. This is from Pablo's group. This is Ben Feldman's group, Stevan's group, Dima Efetov's group. And if I didn't include the plot from your group, I apologize for that. But this is not an exhaustive list. This is also, interestingly, some of this is also seen away from the magic angle. So for example, in this device from Matt Yankovitz, Andrea Young, Corey Dean's collaboration early on, they were not at the magic angle. The twist angle is 1.27. And so they do not see correlated insulators at 0 external pressure, at 0 magnetic field. But interestingly, they do see a non-zero S intercept here. And I will try to come back to this. All right, so there are two scenarios which exist in literature which try to explain the presence of these correlated Chern insulators. So one of them is based on the topology of the twisted bilayer graphene narrow bands in zero magnetic field. So these narrow bands are sketched over here in the so-called band basis. But if you just consider this Hilbert space or subspace of the Hilbert space, you can then find a linear combination of these two bands and rewrite them in terms of a Chern plus and a Chern minus band in each valley separately. And so one possibility for, or one scenario for the correlated Chern insulators which are seen in the experiment is that we are essentially seeing a selective population of these zero field Chern bands. So for example, a state with S equal to -3 and T equal to -1 would correspond to populating a state, one of these strong coupling Chern bands, for example, in valley K, and let's say with spin down, that carries the Chern number -1. And then you can convince yourself that you can construct this sequence by selective population of these bands. So that's one scenario that exists in the literature. There's another scenario which exists in the literature, which is we would start from a non-interacting problem. So we start with the band basis, and before we turn on interactions or before we admix this basis, we turn on an external magnetic field and solve the Bissitzer-McDonald problem, or it doesn't have to be Bissitzer-McDonald problem, some continuum model problem in an external magnetic field, which itself is going to give us a Hofstadter spectrum. And this Hofstadter spectrum is going to have 0 lambda levels, which emanate out of these Dirac points. And because this is a low density of states region, there's going to be square root of B type energy dependence of these levels. And so there's a fairly large gap between the 0th lambda level and the rest of the lambda levels below this. And so you can imagine a scenario in which at S equal to -3 and T equal to -1, you select the valley and you select the spin, but instead of mixing this very strongly with interactions, you just simply fill below the 0th lambda level. And that's also going to give you the same S and same T as this picture. But this is a very different picture because you're definitely not, your interactions are definitely not strong enough to mix the entire band thoroughly to turn them into Chern plus and Chern minus. So these are sort of two extreme limits which exist, and the question is what's going on in the experiments, and can one actually bridge these two using a explicit calculation. So what we do for the purposes of this talk is focus on this minimal continuum model, also known as the Bissitzer-McDonald model, which for a given valley and given spin is a 4x4 differential operator. The upper 2x2 block is the massless Dirac point, massless Dirac Hamiltonian, so is the lower 2x2 block, and then they are coupled by this tunneling matrix, which is spelled out over here with two parameters which specify the interlayer tunneling through the AA regions and the interlayer tunneling through the AB regions. And so now we can apply via a minimal substitution an external magnetic field to this Hamiltonian and then solve this in the lambda level basis. Okay? And that will give us pictures which look like this. So that's our basis. And then we consider Coulomb interactions. We take the Coulomb interactions and we project those Coulomb interactions onto the wave functions that come out of this basis. Okay? And we try to solve that problem. There are improvements on this minimal continuum model, which are discussed in some of these papers. And they are important if you want to understand things like particle hole asymmetry. So this Hamiltonian is almost exact, in fact, the one that I have just written down is exactly particle hole symmetric, and so all of our results will be the same on the hole side as on the electron side. Experiments are not exactly particle hole symmetric, so I will not be able to capture that with this model. In order to add the Coulomb interactions, we need to calibrate them. There's a question of what dielectric constant should one use. And the way we do that is we go to zero magnetic field, consider this twist angle, and in this particular case, we add 0.2% heterostrain. The previous talk discussed the effects of this. And then just simply within self-consistent Hartree-Fock, we compute the chemical potential as a function of density. And the difference between a fully empty and fully occupied will depend on the strength of the Coulomb interaction. And so will these features in chemical potential versus density. And so we adjust the dielectric constant by hand so that we can reproduce the overall scale that corresponds to the change of the chemical potential from fully empty to fully occupied band. So once we fix this, we then solve the problem in the external magnetic field in this basis using the self-consistent Hartree-Fock calculations. This is a busy plot, so let me walk you through this. The 6 panels correspond to 6 different twist angles. We start at a high twist angle. This is the angle that was discussed in the previous talk. For this particular case, we set the heterostrain to 0. The x-axis is the filling of the Moiré band. The 0 is the charge neutrality point, and I'm only showing the whole side because, as I mentioned, this model is perfectly particle-hole symmetric, so it will be redundant to show the electron side. It will be the mirror image of this. The y-axis here is the magnetic field, which is also expressed as a flux through the unit cell, and all of these calculations here are shown up to half flux through the unit cell. We can push these calculations down to 1/12 of flux through the magnetic unit cell. It becomes quite expensive to go below that. Now, each of these points, which are shown here, correspond to at least 6 Hartree-Fock calculations. These are different initial conditions, and we try to make sure that we converge to the same answer. The size of these dots represent the gap we see at the Fermi level. Okay? So the prominent Chern insulators will therefore show up as these streaks through this plot. So as we start at the high twist angle, where at 0 magnetic field we do not find any correlated insulators at any of these fillings, we see strata lines which emanate out of the charge neutrality point, which are also split. This is due to quantum Hall ferromagnetism. But other than that, there are only lambda levels which emanate out of the bottom of the band. You also saw them in the previous plot. But if you look closely, you can start seeing that out of a half flux, there are few streaks that emanate here, and they terminate in compressible states. But as you lower the twist angle, they persist deeper and deeper into this B and N plot. And so the states with a non-zero S are there already significantly away from the magic angle. And you also saw that in the experiment from Matt Yankovitz, Corridina, and Rea's collaboration. And then, as we progress closer and closer to the magic angle, it becomes quite rich. And I will come back to this in later plots. So, so the first question is to ask, in this calculation, we have access not just to the energies, but also to the wave functions. And so we can study the nature of these correlated Chern states and try to answer the question I posed earlier, which of these two scenarios, or is there a scenario in between, accounts for these states. So let's start at a fairly high twist angle, 1.28 degrees. This is the angle where we do not see correlated states at 0 magnetic field. And then let's focus on the S equal to -1. So this is, you just added the first electron into the narrow band coming from the bottom. So in this case, we can, well, what I'm showing here is a solution to the Hartree-Fock calculation at 0 magnetic field at S equal to, at filling factor -3. And this state is compressible. There's no gap in the spectrum. It's a compensated semi-metal. But we see that there is one valley and one spin which separates out from the rest of the spectrum with a Dirac point that doesn't open up a gap. Now, these two plots on the right show the results of the self-consistent Hartree-Fock calculation along this line. And they are color-coded by the same quantum numbers as are shown here at 0 magnetic field. And you can see already from this plot that, for example, for the split-off band, which corresponds to, in this particular case, valley K and spin down, so this is the magnetic moment that is aligned with the external magnetic field, and so it's pushed down, partly due to Zeeman. The 0th lambda level that we are seeing here indeed emanates out of this Dirac point here. And then, for the other 3 flavors, we see the 0th lambda level that emanates out of this Dirac point. Okay? The group of states which then sit below this 0th lambda level now carries a total Chern number -1, and that's how you get T equal to -1 in this, along this line. Okay? Now, this is a compressible state at the 0 magnetic field, and therefore it requires a threshold value of an external magnetic field for us to actually see a incompressible state at finite magnetic field. Our calculations in this particular case only go to 1/12, and so we are already above that threshold. Now, if we then go to s equal to -2 and t equal to -2, something quite similar happens. Although in this particular case, we have 2 of the flavors which separate out, and they're exchange split from the remaining flavors. Again, this is a compensated semi-metal, but now because we have 2 copies of a Dirac point here, and this pocket now is only 2-fold degenerate, it needs to sink deeper in order to compensate for the holes in this Dirac point. And similarly, we see that once the 0 lambda level, once the gap between the 0 lambda level of this Dirac point and the n equal to -1 lambda level of this Dirac point is no longer intercepted by the lambda levels coming out of the minimum of this pocket, we see a gap state. That again happens above a threshold magnetic field. And so that accounts for the s equal to -2 and t equal to -2 line at this value of the angle. And then finally, at n equal to -1, this is now 3-fold degenerate, and so this pocket has to dip even deeper, and therefore the critical field above which we see the incompressible state is higher. But again, a similar story here. And so in this case, although this is not exactly a correlated Hofstadter ferromagnet, it's a renormalized version of this, it's a good starting point to think about these strata lines. So now we lower the twist angle to 1.2 degrees, again, without any external magnetic, without any strain. And we see that the gaps get stronger, these features get a lot stronger, and dip deeper into the magnetic field density plane. Interestingly, in this case, in order for us to understand the results of the self-consistent Hartree-Fock calculation at a finite field, we have to invoke Chern insulators at 0 field. This is a little subtle, so let me walk you through this. So, let's say we start at s equal to -3 and t equal to -1 again. So the spectrum as a function of magnetic field is shown over here. This is the result of a self-consistent calculation in the presence of an external magnetic field. Now this group of states carries a total Chern number -1. And the way we understand it is by solving again the Hartree-Fock at 0 magnetic field. And what we find is that at at the filling factor -3, this turns into a Chern insulator. Now this Chern insulator is not a strong coupling Chern insulator like you saw before. It still has a sizable dispersion of these gaps, and in particular, like the minimum of the gap here is still at the K point. So you're basically gapping out the Dirac point, as opposed to thoroughly mixing everything and turning it into Chern plus and Chern -1 state. And in fact, the split-off bands are still gapless. Now, and then you can actually nicely match the lambda levels which we are seeing in the self-consistent Hartree-Fock calculation to these band features which come out at 0 magnetic field. So, for example, this minimum would correspond to this, maximum here will correspond to this, and again, we can code them by the spin and valley flavor. So for example, the 0th lambda level that we are seeing over here is actually emanating out of this Dirac point. So this state here within our Hartree-Fock is actually the ground state at filling factor -3. Interestingly, the ground states at filling factor -2 and -1 at 0 magnetic field are intervalley coherent states. In order for us to understand the -2 state that we are seeing at finite magnetic field, we realize that we need to stabilize a Chern state at 0 magnetic field. This is not a ground state in Hartree-Fock, but it is possible to stabilize this state. Its spectrum is shown over here. And now you can start noticing that the lambda levels which we are seeing at a finite and interacting magnetic field calculation really emanate out of the band features of the metastable state. So what we are basically saying here is that even though the vertical line here, which is the filling factor 2 Chern 0 IVC state, is present and it's a ground state at 0 magnetic field, already at this fairly small value of the magnetic field, the way to understand this is as magnetic field stabilized Chern state. Okay? And similar thing happens at s equal to -1 and t equal to -3. All right, so this is sort of an intermediate value of the angle. And to make this more clear, let me show you the density matrices. So these correspond to the wave functions that we obtained from these calculations. And again, focus on these lines. So at filling factor -2, the ground state is an IVC. And indeed, following this vertical line, so Chern equal to 0, t equal to 0 line, we see intervalley coherence. This is consistent with what we see at 0 magnetic field as well. However, if we look at this -2 state, the density matrix looks completely different. The intervalley coherence is lost, and this is really the proper way to think about it is as a magnetic field in stabilized Chern state. Now, if we lower the angle further to 1.05, we find features which do not look like the features that are seen in the experiment. So, for example, we see although we still see some of these lines, we see others which are absent. So, for example, we see a strong feature at s equal to -2 and t equal to -1. And that is not observed in the experiment. We understand this as a Landau quantization of the strong coupling spectrum. So, in particular, the 0-4 line here, which was present in the earlier calculations that I showed you at larger twist angle, is missing, although it is present in the experiments. Now, the -2,0 line, so the vertical line here, is an IVC, so it's a strong coupling state, but the -2-1 line, this one, just simply corresponds to depopulation of a lambda level of this IVC. It is a prominent state with a large gap, but it is missing in the experiment. At -2, at low magnetic field, this is actually quite weak, and only above a threshold field do we see it as a strong insulator. It is weak at low field because it's essentially population of lambda levels of the IVC, and then as the field gets stronger, it turns into a Chern state. The -3,0 is still a strong coupling Chern +1 insulator, but with one lambda level depopulated. Okay, and then -1 is a strong coupling Chern insulator, and we can understand the sort of fan which emanates out of this as depopulation of lambda levels of either Chern plus or Chern -1 insulators. Now, so as I said, this doesn't look like most of the experiments, although it is similar to the scanning compressibility data in a likely HBN aligned twisted bilayer graphene from Pablo and Amir Jacobi's collaboration, particularly on the electron side. And so perhaps when the narrow bands are actually isolated from each other due to this alignment, some of this physics actually persists down here. Now we can do these calculations in the presence of an external heterostrain as well, starting from a large angle, and the features look similar, although the details as we come closer to the magic angle are different. And in particular, we do see an emergence of the IKS states at finite magnetic field, which, as we increase the magnetic field, turn into states which are not intervally coherent. Now, so far I have been talking about the states where S plus T is equal to -4, by particle Hall symmetry also +4, but we also see states which have fractional S. So these are, this would emanate out of -1.5 or -0.5. And so let me just quickly go through this part and focus on the fractional S and integer T states. So these states break translation symmetry. They're stripe states. We highlight them here using these lines. So, for example, this one would have an intercept -5/2 and a slope -1. This is S equal to -3/2, slope -2. And this one is S equal to -1/2, slope -3. There are others which have 1/3 intercepts, but let me just focus on this. The plot here shows the local density of states computed for the spectrum of this particular state just at the edge of the conduction band. And so you can see that there is a doubling of the unit cell. And we can actually understand these Chern numbers by thinking about the parent state, which was -3, -1 that I discussed below, and then adding half an electron per unit cell that crystallizes. It can be a bit more complicated because that crystallization at low field can also be accompanied by intervalley coherence, but that's the basic way to think about it. It's basically -3, -1 state with an extra half an electron crystallizing. And similarly, for this -3, -3 halves, -2, and -1/2. Now, Xiaoyu was at a conference where he was presenting this data, and a student from Xiaodong's group was there as well, and they started talking to each other and realized that, in fact, this is already seen in some of Xiaodong's data. And so in particular, what they noticed, among other interesting things in this data, is that in this device, which was at 1.03 degrees and included a WSE2, these fractional S states, precisely with the sequence, were also observed. So this is S equal to, unfortunately, this is flipped notation. So this is S equal to -5/2, T equal to -1, S equal to -3/2, T equal to -2, S equal to -1/2, and T equal to -3. Okay? All right, so I think I'm actually at the end of my allotted time. Okay, I have 1 minute left, so let me channel my friend and collaborator and ask for 3 more minutes. And talk about maybe twisted MOT2. Very, very quickly, we all know this is an extremely interesting system. We have these pockets also in the K and K' points, which of course have a gigantic gap, and upon twist, there's a very interesting set of Moiré bands which host correlated Chern insulators, including fractional Chern insulators. The narrow bands carry Chern numbers. This is the original calculation from Feng-Cheng Wu and Alan McDonald's group. This is a calculation which is perhaps a little bit more close to the microscopic calculation at 3.89 degrees from 3 different groups, also seeing this particular assignment of the Chern numbers at this particular angle. Now, 3.89 is significantly larger than the twist angle for the MATBG, so magic angle twisted bilayer graphene. And so in order for us to study the physics at finite external magnetic field, we have to thread a lot less of a flux through a unit cell to access magnetic fields that are shown in this plot. Now, the prominent integer states, which are seen here, correspond to s equal to -1 and t equal to -1. And this is the same in the Washington's group, University of Washington group, Cornell group, also Shanghai's group. And one interesting thing is that the s equal to -1, t equal to +1 is missing for this orientation of magnetic field. And so one of the things that we wanted to answer is, why is that the case? This is technically a bit more challenging to do, because a full flux to the unit cell here will correspond to 176 Tesla. And so in order for us to go below 9 Tesla, we really have to push the numerics. We have a procedure to do this. And so let me just show you the outcome of this calculation. Again, this is a bit of a busy plot, but it shows the result of a self-consistent calculation for twisted MOT2 in the absence of a perpendicular magnetic electric field, although we have it in the presence of an electric field. And there are two candidate states that you can consider at -1, -1. One is the obvious one. You populate the valley with the correct Chern number, and then there's a giant gap, and that gap will not collapse as the magnetic field goes to 0. But there's another candidate state, which in principle you can stabilize. It seems silly to do that, but it is possible to consider a state in the wrong valley, the Chern +1, and in the external magnetic field, that's going to get Landau quantized, and you depopulate two Landau levels of that state. That's also going to get you to be at -1, -1. The question is, which one of these has a lower energy? And similarly, -1 +1 state would be, again, the other valley with two Landau levels populated. We can also consider the natural state for -1 +1, which would be the valley K prime, and that would have a large gap. So the question is, what is the energetics between these states, and how is it selected? I'm just going to show you the upshot of this story. What we found is that in the absence of Zeeman coupling, we would stabilize the large gap states both at -1, -1 and -1 +1. -1 +1 is not seen in the experiment. However, when we include the Zeeman coupling and do this as an adjustable parameter, we find a near degeneracy between these states. And if we use the value that is extracted from ab initio, namely the orbital G factor 9, the full lambda G factor of 9, so this includes spin, then in fact we do find that a small gap state is stabilized along -1 +1. So we can actually explain the missing state. Now, given that I've already overstayed my welcome, let me just stop here and thank you for your attention.
Questions?
Yeah, thank you for the very beautiful results. So I have a question about the first part. What epsilon, like the dielectric, did you use in the in the TBG calculations?
Yeah.
That
So I'm getting to this. There's a slide on this. Oops. Yeah. So we used this value, and the logic behind that was to match the change in the chemical potential between the completely empty and completely full narrow band to the measured value. As you, I'm sure you know, if you were to choose lower value of the dielectric constant, these features would get a lot sharper, and this change would be different. So that's how we calibrate it.
But this is Oh, okay. Okay. So having the sample encapsulated or not can affect this, right? And this could effectively mean that the data you think is like the calculation you at the magic angle could be effectively at larger angle, because I mean if you push epsilon down, that's like increasing the bandwidth. So this could explain the why you see this one line that is not seen in encapsulated data is if epsilon is a bit larger. If you take a larger epsilon, that
means we have weaker interactions.
Yeah, yeah.
You could explain what?
That that would mean that your data at the magic angle is effectively describes a larger angle.
So I think it's the other way around. So at our 1.05, the BM narrow band is too narrow, even for this value of epsilon.
Yeah, yeah. If you take a larger epsilon.
Yeah. So sure, but we have this measurement.
Yeah, so what I'm saying is it does depend on the value of what value of epsilon you take, whether the actual magic angle samples fit the what you think is at 1.05.
Right.
Yeah.
So my thinking on this is that the BM model is an oversimplification. There are the terms which we know are present, high order gradient terms, and the bandwidths one gets due to those extra terms are not as narrow as the BM model would give you. So my take on this is that if I stick with the BM model, which we did in this calculation, I get the bandwidth perhaps of the more accurate model at a higher angle.
Yeah, okay, thank you. Yeah.
You're welcome.
Yes, thank you very much for the talk, Oskar. I had a question about the charge density wave slide. So is there any particular reason that, one, you only saw the 1/2, and two, why it seemed to be stabilized by the magnetic field? It looked like the gap was getting bigger as you increased the magnetic field. There's some sort of nesting going on?
I don't think it's nesting. I think we are past any weak coupling limit. But I don't have a simple explanation for why this 1/2. I mean, to 0th order, as I said, you can think of it as minus, let's say the simplest one, -3 -1, which is your correlated Hofstadter ferromagnet. You populate below the 0th lambda level, although there's a stronger normalization. And then the extra half of the electron goes into a stripe. Mm-hmm. Now, that's the simplest version of that state. You can also have intervalley coherence between the two, but maintaining S and T.
And correct me if I'm wrong, but the only similar states also have the 1/2 intercept too. There's no evidence of similar states with other fractional intercepts and integer Hall conductances, right?
No. So there are also third intercepts.
Oh, but you do not see any of those?
No, we do. We see
you
them,
do? Okay.
We see them in the calculation, and they're also seen in the experiment.
I see. Thank you very much.
You're welcome.
So thank you for a wonderful talk. So I have another disorder question. So would it be possible to include disorder in your approach?
It's a long and complicated answer to that question. So along what we heard in the previous talk, I think what we need to know is what's the structure. The structure may have twist angle inhomogeneity, and as you discussed previously, is likely happening on larger length scales. It is possible to take that as an input of a more sophisticated model, which we have. It's a model in which you do not require periodicity, based on the idea that there's a gradient expansion that gives rise to these type of continuum models. So it is possible to include that type of longer range inhomogeneity into this and an external magnetic field, but we have not carried out, I think this would be quite complicated to carry out calculations such as this, but there is a framework within which this is possible.
Thank you.
Yeah, you're welcome.
Oh, in your last slide regarding the MOT2, if we were to assume that the Valley G-man vector, the G factor, was larger than 9, how would you expect the energetics to compare between the two states that you compare?
It's even better. So so thank you for asking that question. Sorry. Right. So let me start with the no G factor whatsoever. Okay, so in that case, what we find is that the lower energy state at -1, is a state with a large gap. So you polarize your holes into the correct valley with the correct Chern number. But then if you look at -1+1, the lower energy state is also the state with a larger gap. Okay? Now it turns out that the spins of these two valleys are, as you know, probably locked to the valley. And so for this orientation of the magnetic field, including the Zeeman and the orbital G factor, will actually start stabilizing the valley K. So this blue curve is going to start coming down. And as you increase G in this calculation, this blue curve is going to cross the red curve. Once it crosses, you see the state that wins along the -1+1 line is a integer quantum Hall state of this state. Okay, so it naturally has a small gap. If you go above G2, this splitting gets just larger, and you stabilize the state even better. Now, you didn't ask this, but it is in my slides. So there's this beautiful data from Andrea's group where they measure the magnetic moment of these devices. And so since we have a way to compute the total energy as a function of magnetic field and as a function of particle number, we can extract the moments. This is not published, but we can do it at fairly low magnetic fields, and then we interpolate to 0 magnetic field using this calculation. This is now with this large G factor. The values that we get are not exactly the ones that they see, but they are not far. So, for example, here we see something above 6, they see something about 9 Bohr magnetons per unit cell, and this is maybe 3.5 there at about 6. So, okay, it doesn't completely match. You may need a larger G factor, but actually most of this is coming from this large G factor. Yeah.
Hi, Oskar. Thanks for the very, very nice talk. I have a question about your chemical potential dependence in Hartree-Fock with respect to charge density. Mm-hmm. It seems that it has some non-monotonicities.
Yes.
And could you briefly explain how that happens?
Yes. So that's just negative compressibility. Once you have interactions, you can get. I mean, I'm sure you understand this is not the true thermodynamic compressibility, but it's the compressibility that's measured. So that's just that. You can capture that within subconsistent Hartree-Fock. So I think what you saw was that the chemical potential was going up with density and then had a dip. So this negative slope here just corresponds to negative compressibility. That's also seen in the data. I can show you that, yeah.
Thank you.
Yeah.
Okay. Let's take one last question.
How do the thermodynamic gaps in the twisted bilayer graphene calculations at finite field compare to those extracted from compressibility measurements?
We are bigger. The calculation is bigger than what's in the experiment. Unless you look at the compressibility data from likely HBN aligned from Amir Yacobi's group, there it's still larger but comparable.
How much bigger when you say bigger? Like factor 2?
I don't remember the exact factor.
Okay.
Yeah, we can look at it.
Thanks.
Yeah.
Great. Let's thank Oskar.